Hello, this is a lecture series for Chemical Engineering Thermodynamics. We are at part 2 of lecture 4A, which is about second law of thermodynamics. In the last lecture, in the part 1 of lecture 4A, the introduction to the second law of thermodynamics was given. And in a sense, we talk about the difference between heat and work in the eyes of the second law, and also in terms of directionality for the change of the process. In this lecture, I will talk about the derivation and definition of entropy. In order to understand how entropy was derived, you need to understand the engine or the steam engine first. Okay, in steam engine, basically we use steam to produce work, and how it's work is done in cycle. There are four main elements or four main machine inside this steam engine. We have a tank storing for water, and then a pump, a boiler, turbine, and condenser connected as a cycle like this. Let's start with in the tank. If inside the cycles we have water as our medium, water in liquid phase would be pumped into a boiler. If we look at the pump itself, this is a picture of a pump. Basically, it is a blade that is rotated by applying work. So if you apply work to drive this impeller, this impeller would rotate and push water out to this discharge. At the same time, it will create suction for water entering into the pump. Okay, so basically, in terms of energy, we need to supply work into pump so that the pump can transfer liquid from one side to another. Okay, this kind of work can be mechanical work if you manually rotate the pump, or nowadays we use electricity, which is non-expansion work. Okay, then the pump will enter a boiler. Within the boiler, you can imagine the boiler to have a series of tubes in which water flows inside. Outside of the tube, there's a combustion. You supply fuel and make a combustion gas. That hot gas would transfer energy into water inside. Okay, and as the water heats up, the temperature rises, and then until it reaches the boiling point, it will turn into steam. If once you get the steam and the heat still supplied to the steam would change from saturated steam into the superheated steam, just like what we discussed in lecture 3. Okay, so in terms of energy, high temperature surrounding here supplied energy into the water. And if we assume that this energy, the energy of this combustion gas is so much, you have continuous supply of fuel into the boiler. So even though some energy is transferred from the hot gas here into water, the temperature of the combustion gas remains the same or remains unchanged. In this case, we can imagine that the energy of this surrounding highlighted with the yellow area here remains constant, even though it gives away some energy to the water. We call this kind of thing as hot reservoir. Okay, the term reservoir means whenever you do something with it, even though it has some transfer of energy out of it, the temperature remains the same. Even though it receives some energy, temperature remains the same as well. Okay, so if I draw a hot reservoir here, this yellow area is highlighted as the hot reservoir, is the source for energy to be transferred into water in the boiler, and heat will be drawn from hot reservoir into the boiler so that water entering the boilers receive energy and can be converted into steam at the outlet of the boiler. Okay? Once steam passes through this turbine, the turbine here basically is a series of impeller that can be rotated by the flow of the steam. The steam coming into the turbine has high energy. Perhaps it has high temperature and high pressure. That high pressure can push this impeller to rotate and produces work. So you have work leaving, or the turbine itself produces work out of the rotation of the shaft. The instrument in reality is a series of blades connected in series like this, because gases entering the first blade pushes the first set of the impeller to rotate, but still gas still have energy left, so you can create a series of impeller or series of blades like this, so that you can employ the turbine as efficiently as possible. And once the steam pushes the blade long enough, then it loses energy. The pressure will be lower, the temperature will be lower, and steam going out of the turbine should have lower energy than the steam going into the turbine. You can also look at the turbine, or you can do the energy balance around the turbine. Energy coming in must be subtracted by work leaving the turbine, so that the energy of the steam coming out is supposed to be lower. Okay? Then the steam would enter a condenser, which is the instrument or equipment to condense all the steam back to liquid water. Inside there's a pipe, the blue pipe here, in which we have cooling water flowing inside. So our steam, this steam here is in the white area or the gray area here of the instrument. It passed through from top to bottom. Along the way, the temperature would be reduced by cooling, by the heat transfer out of the steam into the cooling water. So again, if I continuously supply this cooling water, we can imagine that temperature of this cooling water remains constant, and call this cooling water to be cold reservoir. So we can draw the cold reservoir here, and can imagine that there will be heat transfer from the steam inside the condenser in this white area to be transferred into the cold reservoir, so that all the steam will be condensed into liquid water. And the reason that we need liquid water is that any gas passing through the pump would make the damage to the impeller of the pump. We cannot use the pump to transfer gas from one side to another. We need the gas to be converted into complete liquid, so that pump can be used. Okay. So at the end we have water coming out of condenser entering the pump, and we complete the cycles. So in this case, if the cycles here or the engine here is operated under steady state, so that means water leaving this storage tank supposed to be the same amount in terms of flow rate as the water entering return back to a storage tank. So at steady state, the tank here may not be needed. So we can just neglect the storage tank for the moment, for the sake of simplicity. Okay. If you look at the engine and you draw a box around the engine, you can see that there's a work going into the pump, and then there's work produced from the turbine, and then there's a heat transfer from the hot reservoir into the engine, and then heat is transferred out of the engine to cold reservoir. If I combine work on the left hand side to the work produced from the turbine, this amount of work is supposed to be a little bit lower than what was produced from the turbine, and we call this one the net of the work produced. Okay. If I label this heat to be QH and this heat to be QC, you can see that it seems like my engine here can convert heat into work. Okay. However, if you look closely, you will see that W here cannot exceed QH. According to the first law of thermodynamics, if you imagine one group of energy entering the system as QH, that amount of energy cannot be, or the amount of energy produced as work here cannot be greater than the amount of energy entering the system. So we can conclude that W cannot exceed QH. At the same time, according to the second law, we cannot have QC to be 0. Why do I say that? Because if QC is 0, that means QH is equal to W. In other words, it means that you can convert heat into work 100%. But from last clip, from part 1 of lecture 4a, we said that work is more valuable than heat, so therefore we cannot fully or completely convert heat back to work. Okay, so in that case it means that QC cannot be 0. Alright, now if I define efficiency of an engine here to be W, which is the energy produced, the output energy here, divided by entering energy QH. This is what we want. The work is what we want, divided by what we supply to an engine. This is defined as efficiency of this engine. You should see that according to the energy balance, W can be written as QH subtracted by QC, because input must be equal to combination of output here, and then eventually you get 1 subtracted by QC over QH as efficiency. From this formulation, you will see that according to these two criteria, QC cannot be 0, so therefore efficiency here can never be 100%. Also, W cannot exceed QH, so this efficiency here, according to this equation, can never exceed 100%. So the steam engine usually have efficiency lower than 100%. Okay, and from this equation you should also see that this equation has nothing to do with elements inside the engine. It has nothing to do with flow rate of water inside, and it has nothing to do with how each element was constructed. It is about energy entering the engine and energy leaving the engine. Okay, if we consider water, okay, and now just look at the water. Water is converted from one state to another. So if I put the label state 1, 2, 3, and 4 to represent various states of water, and now it can also be something else rather than water. We can use any kind of fluid instead of water. So if I use gas instead of water, then there will be no phase change within the cycles. Instead, gas would change from state 1 to 2, 3, and 4 and back to state 1 again. This can still be used as an engine. Okay, now whenever we use gas inside these cycles, the cycle is called Carnot cycles. Okay, and if I put properties of gas in each state. Let's say we call this state P1 V1, P2 V2, and so on. Okay, if the gas is ideal gas or any kind of gas, we can look at properties of gas, or we can track the change of gas properties in PV plot. This is what we did in lecture 2 and lecture 3. And in lecture 3, we learned that whenever we have PV plot, there's a line called isotherm along this line temperature remains constant. Okay, so in this cycles here, from state 1 to state 2, the temperature remains constant at TH, and this TH will be the same temperature as the temperature of hot reservoir as well. So my first stage here, state 1, I'm supposed to have the state located on the isotherm TH, and P pressure here is P1, volume here is V1. The change from state 1 to state 2 for the Carnot cycles is isothermal expansion. So the word isothermal means constant temperature. So that means the change from state 1 to state 2 must go along this isotherm TH. The word expansion means the volume of the gas supposed to get higher. So this point is supposed to go to the right hand side of this graph. Okay, so I change from state 1 to state 2. That means the state here in the PV diagram supposed to go down along TH isotherm to state 2 like this. One thing that you might notice and you might get question is that from 1 to 2, temperature remains constant at TH because it is isothermal. However, this temperature TH is exactly the same as the temperature of the hot reservoir itself. How could that be possible? Because from the very first lecture, I told you that heat can be transferred only when temperature of the system and surrounding are not the same, right? So if I like heat to be transferred from hot reservoir into the system, the temperature of hot reservoir cannot be the same as the temperature of the system. So what is wrong here, or what is happening here? In detail, you need to understand that from state 1, if gas has high pressure, okay, the expansion takes place first. So when the expansion takes place, the temperature of the gas drops just by a little. So just look at the ideal gas, PV equal to RT, or P1V1 over T1 equal to P2V2 over T2. If the pressure is reduced, you expand the volume. Volume is increased. The temperature must be dropped. Okay? When the temperature of the gas is dropped by a little, that small temperature drops should induce the temperature difference between temperature inside the system and the temperature of surrounding. Okay, therefore the heat will be driven from surrounding into the system. Once heat is transferred into the system, temperature of the gas rises again until it reaches TH, and then the heat transfer will be stopped. If the amount of temperature drops is small enough to be able to be assumed to be constant, then we can make approximation that the change from state 1 to state 2 is isothermal. Okay? From state 2 to state 3, the Carnot cycles indicates that this step must be adiabatic expansion. So again, expansion means that volume is supposed to be increased, but this time it is adiabatic. According to the first law, delta U equal to Q plus W, when it is adiabatic, Q is equal to 0. When you have expansion, that means the internal energy is supposed to be lower, right? When internal energy is lower, temperature is lower. So this time you have to go from TH into TC. So it goes from here to here, from state 2 to state 3 by leaving the TH isotherm and entering TC isotherm. Okay? So therefore I put it here as cooling. The gas would cool down. If you recall the lecture 2, when we have PV plot, the area under the path that the system took can be calculated into work, right? because work is integral of PdV. So the highlight area here represents work associated with expansion. Remember that from state 1 to 2, that's expansion. 2 to 3 is also expansion. So the total expansion work can be calculated based on the area underneath here. Okay? Then from state 3 back to state 4, that's isothermal compression, which is opposite direction of state 1 to 2. Okay? Both of them are isothermal, but this time it is isothermal compression. Since it is isothermal at Tc, the state would move along this isotherm Tc. Since it is compression, the volume is supposed to be lower or smaller. So we move from here, from 3 to 4, along the isotherm Tc like so. And then from 4 to 1, we just close the loop. The step from 4 to 1 is adiabatic compression, which is translated to heating, because when it is adiabatic, Q is equal to 0. When you supply work to compress the gas, internal energy of the gas will be increased according to the first law, and temperature, which is indicator of internal energy, is supposed to be increased as well. So you return from state 4 to 1 and you close the loop here back to the original initial state 1. Okay, if you notice from 3 to 4 to 1, these two steps are compression. So the area underneath this graph is supposed to be compression work. Okay, in this case, expansion work is greater than compression work, which is a little bit different than what I mentioned in lecture 2. This is a special circumstance when we discuss about the engine. Okay, so therefore this engine can produce work in terms of expansion work that we can use. The amount of work produced by this engine can be found just by take the compression work or expansion work subtracted by compression work, and that can be represented by this green area. This is the net of the work produced by the engine. For Carnot cycles, the special thing is that all the steps here are reversible. Okay, in order to obtain maximum expansion work by using minimum compression work, we learned from lecture 2 that the maximum expansion work, minimum compression work could be obtained when all steps are reversible. So once again, if you put a box over this engine, you can see that you can produce work by supplying some heat to the engine, and at the same time some part of the heat must be released from the engine, and then you got some work produced from the engine itself. Okay, now just to make things simple, if we use Carnot cycles and assume that the gas inside is ideal gas, in that case, from state 1 to 2, which is isothermal reversible expansion, according to the first law, du equal to del Q plus del W, since it is isothermal for ideal gas, internal energy is a function of temperature only. So therefore, when the temperature remains constant, there will be no change in internal energy of the ideal gas. So du becomes 0 here. Rearrange the equation. If you integrate the del here from small amount of heat to the total amount of heat in process 1 to 2, you get Q equal to minus W. And then from the reversible work, dW by itself is minus PdV. So W is integral of PdV, and minus would disappear from here. Okay. Then you can replace this pressure by using ideal gas law. P equal to RT over V, and then R is constant, temperature T is constant because it is isothermal at TH here, and then you only have 1 over V dV. After integration, you get logarithm of V2 over V1. In this step, heat associated with step 1 to 2 is called QH, and temperature is constant at TH, so I put QH and TH here. In similar manner, state 3 to 4 is also isothermal reversible, but it is compression. Since it is also isothermal and reversible, the equation obtained from 3 to 4 is supposed to be in the same form as from 1 to 2. The only thing different is that Q here is called QC, and temperature here is called temperature TC, and state is changed from 3 to 4, so volume here is supposed to be V4 over V3. Okay? If you take these two equations, take the first equation divided by the second equation, you get this relationship, and you will keep this relationship in mind for a while. Now, if we focus on path 2 to 3, which is a diabatic reversible expansion, from the first law, you can got the first law like this. Since it is adiabatic, Q becomes 0. From ideal gas, U is function of temperature only. du can be found from integral of Cv dt, or du equal to Cv dt, right? While the reversible work, dw would equal to minus pdv. So you get this relationship. If you move, or if you replace pressure by ideal gas law, P equal to RT over V, and take RT to the left hand side, you can get this equation, and then you can integrate it from state 2 to state 3. That means you integrate it from TH to TC. Okay? On the right hand side, you integrate it from V2 to V3, but you have a negative sign here, so therefore the logarithm ratio will become V2 over V3. Keep this in mind for a while, and then similar equation should be obtained from path 4 to 1 because it is also adiabatic reversible. So you obtain this similar form of equation but changing from state 4 to state 1. So therefore integration must be done from TC to TH. Okay, you can see that this term and this term are similar. In order to make things the same, you just flip this integration limit on the right hand side. The ratio will be flipped as well. Okay, from these two relationships, then you can get that the volume ratio V2 and V3 should be the same as V1 and V4, or in other words, V2 over V1 equal to V3 over V4, so that we can get this relationship in the same manner as this ratio here. Okay, so if we take these two equations together, you will end up with logarithm ratio here supposed to be gone. Then you get QH over QC equal to minus TH over TC. Okay, and then rearrange this equation to get this ratio added together to be 0. Now, this is the equation that Carnot, which is the inventor of this cycles, he observed this equation. Okay, and he realized one important thing. Now, if you look at the system itself is gas inside the cycles. It undergoes the change from state 1 to 2 to 3 to 4 and back to 1 again. If we want to calculate the change in internal energy of the system, of the gas itself, you can expand the delta U here to be delta U of 1, 2 plus 2 3 plus 2 3 4 and 4 1. Each delta U here is a delta U of each step here. Okay, so when you combine change in internal energy of each step, that should equal to the internal energy change of the whole system. Okay, so going this way is the indirect path. Going from here, the delta U of the system is calculated as the direct path, and we learned from lecture 2 that they are the same. Okay, delta U1 2 2 3 3 4 and 4 1 can be expanded as U2 subtracted by U1. Delta means change, right? Delta U1 2 is a change from state 1 to state 2. So mathematically you can get U2 subtracted by U1 and so on. And you see that U1 here and there cancel out, 2 here and here cancel out, 3 and 4 will be cancelled out as well. So eventually mathematically on the right hand side you get 0. Okay, so according to math you should get delta U of the system equal to 0. But according to physical meanings, you can say right away that in this case delta U of the system must be 0 by itself without doing calculation at all, simply because this is cycles. You start from state 1 and you go somewhere else and return to state 1 again. If you calculate delta U of the system, the change of the system, in this case it seems like the system does not change at all because it stays at state 1. Once it goes somewhere it returns to original state, so it seems like it does not change at all. Without any change, delta U of the system is supposed to be 0. Okay, you can claim like this, and you can see that finding from the indirect path and finding from the direct path are the same because internal energy is state properties. Okay, if you repeat the same calculation from heat, you will not get 0 because heat is path properties. But if you take this equation, Carnot realized that this equation gives 0 as well. Okay, in similar manner as delta U. So that means whatever inside this red box, you can write this equation as delta of something equal to 0, and this something must be state properties in the same manner as delta U. Okay, because for the system going somewhere and going back to original position, original state, and relationship end up with the combination of whatever we have on the left hand side equal to 0. It means that inside here has no change, consisting of the fact that it's supposed to be state properties. It is the same behavior as the change in state properties. So therefore this ratio must be state properties. This is what Carnot realized, and he called this ratio to be entropy, or S. Okay, so by definition delta S was defined as heat over temperature. But please keep in mind that since Carnot cycles was defined so that all associated paths are reversible, so this heat must be reversible heat. Okay, this is very important to keep in mind that this heat must be reversible heat. So if you take small change in entropy, the delta here would turn into differentiation, and this net heat would turn into small amount of heat, del Q reversible here. So this sometimes can be written as the definition of entropy. Okay, so ds equal to del Q reversible over temperature over T. After integration on the left hand side, once you integrate it, you get delta S, the total change in entropy in the system. On the right hand side, integration of this small amount of heat, you should get net of the heat transfer. Okay, keep in mind again, this is reversible heat. Now let's bring back the cycles. From this equation, if each ratio is defined as delta S, okay, we can say that the delta S of the system was equal to QH over TH of the system plus QC over TC of the system. Okay, so basically you write this equation for the system part. Each term can also be called delta S, H or C of the system. So this is ratio here is delta SH. Consider at the hot reservoir here, and this part is here. Okay, the combination of these two, you get these two terms, and these two terms combined should equal to 0. Okay, according to here. If you zoom in this area, in reality, you have gas inside the system here. The gas is considered a system. So this is the gas. This gas is heated up basically by contact with hot reservoir. So we have hot reservoir in contact with our gas. Okay? And according to what we discussed earlier, there must be heat transfer from surrounding into the system with amount of QH. And ideally, for Carnot cycles, the temperature of the surrounding and temperature of system are the same, and we call that TH. But just to be clear, let me call this one TH of the system and TH of the surrounding. Okay? If we consider that the cycles is reversible, so all paths are reversible paths. Okay, the surrounding, the change in entropy of the surrounding can be written in the same manner. So it's a ratio of QH over TH, QC over TC, but this time I use surrounding here just to say that this equation is written for surrounding, and this ratio can be called delta SH of the surrounding. This one would be delta SC of the surrounding. Okay? Whenever we have reversible process, it means that along the way you can reverse the direction back at any time. In order to achieve that, the temperature of the surrounding and the temperature of the system must be the same. Okay? So we can get this criteria here for the reversible cycles. In order for the reversible cycles to take place, the temperature of the system, the TH of the system, must be equal to the TC, to the TH of the surrounding. Okay? And therefore, you can get this ratio. This heat here, QH, is amount of energy transferred from surrounding to the system. So QH here and QH there are essentially the same thing. Okay, so this is this red arrow, and I put absolute here just to prevent any confusion regarding the sign of the heat. Just consider magnitude of the heat only. So if TH of the system is the same as TH of the surrounding, this ratio must be the same. And therefore, this ratio is called delta SH. Okay? Delta SH of the system and the surrounding must be the same. In similar manner, if we consider at the cold reservoir, you get the contact between system gas to the cold surrounding, cold reservoir here, and the transfer of heat is called QC. For reversible process to take place, these two parts supposed to share the same temperature, and we call that TC, but I put TC system and surrounding just to be clear. But you know eventually that TC of the system and surrounding are the same for reversible process. And therefore, the ratio QC over temperature must also be the same, because this QC and this QC is essentially this QC, this arrow, okay? And this ratio is called delta SC. They are the same. Okay? Now if I look at this QH highlighted in blue, this QH, if we consider the system, okay, the system here receives energy as heat. Heat is transferred into the system, so the system receives energy. According to our notation long time ago, we can say that it is positive. It makes energy of the system to increase. Okay, so I put the positive here, just saying that this blue QH is positive. On the other hand, if you look at QC from the system side, the system loses energy, so QC must be negative. Therefore, delta SH here is supposed to be positive, and delta SC here is supposed to be negative. Okay? And you can see that one is positive, one is negative, and when you combine them to be zero according to this relationship, it means that the magnitude of these two are the same. Alright? For surrounding, the QH highlighted in green, this is heat transfer out of the surrounding here. Okay? So if you focus on the surrounding loses energy. So in the aspect of the surrounding itself, this QH, the green QH, supposed to have negative sign because surrounding loses energy. But the QC here, the surrounding gains energy. So I'm going to put positive sign here to represent QC for the sake of the surrounding. And therefore, this delta S of the surrounding SH and SC must be negative and positive respectively. Okay? Now, if you consider this pair SS, SH system and surrounding are represented by this relationship, they are the same. Okay? And this SC of the system and surrounding are represented by this relationship, they are the same. So if these two combined are equal to 0, that means delta S of the surrounding, these two terms combined, must be 0 as well. Okay? So for reversible cycles, change in entropy of the systems and change in entropy of the surrounding, both are equal to 0. What about if the cycle is not reversible? If it is irreversible, what will happen? Let me remove this sign first, okay, and let's discuss. For the change from state 1 to state 2, okay, I'm saying that there's still a change. But the change here, the process is irreversible. That means along the way here, you cannot turn back. In that case, it means that the heat here continuously supply from surrounding from system. You cannot reverse this heat back from system to surrounding anymore. Okay? So that occasion will happen only when temperature of the system is lower than temperature of surroundings. So imagine things like this. If I have surrounding with slightly higher temperature and the system, the heat will continuously supply in this downward direction. Okay? you cannot reverse the direction back. But if you want the process to be reversible, that means these two temperatures must be as close as possible so that we can reverse the direction back at any time we like. Okay? So for irreversible process, the only conclusion that we can make is that it will happen only when temperature of the system here is lower than temperature of surrounding, so that Q would go downward all the time, constantly, without being reversible. Okay? So by second law, this relationship was established, okay, from the word irreversible process. Then, since the denominator here is smaller than the denominator there, these two Q are the same thing. So therefore, this relationship is supposed to get greater sign here. And therefore, delta SH of the system is supposed to be greater than delta SH of the surrounding. On the other hand, if you look at the cold reservoir, in order to make this process irreversible, the temperature of the surrounding must be lower than temperature of the system at all time. Or in other words, the system is supposed to have higher temperature than the surrounding. So greater the temperature here always, so that the process will be irreversible. Okay? So therefore this ratio should have the less than sign here, and delta SC of the system is supposed to be smaller than delta SC of the surrounding. Then this relationship, you still get delta S of the system equal to 0 still. Why did I say that? So think about this closely. Delta S of the system means that the properties of the gas, the pink gas here, still 0, because it starts from state 1, going through state 2, 3, 4, and back to state 1 again. It doesn't matter whether the path that it takes will be reversible or irreversible, as long as entropy is state properties. When it returns back to original position or original state, there is no change in entropy at all. Delta S of the system still remains 0, even though all paths are irreversible now. Okay? But this term, on the other hand, SH of the surrounding, will become less negative. Why? Why it is less negative? If you look at this term, okay, this relationship, it is said that delta SH of the surrounding is less or smaller than the delta SH of the system. So the magnitude of this term is smaller than magnitude of this term. Okay, it's smaller. But by the sign it is negative, so therefore it should be less negative. On the other hand, this term, if you consider this relationship, delta SC of the surrounding is greater than delta SC of the system. So comparing between these two, the magnitude of this term is supposed to be larger than the magnitude of this term, and the sign here is positive. So I can make conclusion that this term must be more positive. Okay? Then this one becomes less negative, this one becomes more positive. These two combined can no longer remain 0. So the summation of these two terms must be greater than 0 for irreversible process. Okay? So the red letters here occurs when the processes are changed from reversible to irreversible. So if you combine the system and surrounding together, it is called the change of the universe. Sometimes it is called delta S total. Okay? So in this case, this one is 0, this one is greater than 0. The delta S total is supposed to be greater than 0 For the reversible process, on the other hand, both delta S system and surrounding are 0. So delta S total is supposed to be 0 as well. So you see that in this case, okay, both cases you have changed. The media changes from state 1 to 2 to 3 to 4 and back to 1. There are changes inside, okay. So it is consistent with the statement of second law that the isolated system spontaneously change to the state with increased entropy. Okay? So as long as there's a process, as long as there's a change, and the change is spontaneous, then the entropy must be increased. So if the change is reversible, it is 0. If the change is irreversible, it is increased, and then it is greater than 0. Okay? So the derivation of delta S or entropy according to Carnot cycles is still consistent with the statement of the second law. However, you need to consider both system and surrounding in this case. Okay? In order to use this statement, both system and surrounding entropy change must be calculated and combined. So in short, for spontaneous process, the delta S of the universe or total delta S total must be greater or equal to 0. Again, if it is 0, it means that the process is reversible. If it is greater than 0, it is irreversible. But both of them are spontaneous process. Okay? Now, if we look further from the first part of lecture 4a, I told you that entropy is indicator of chaotic dispersal of energy and mass. Okay, this is what the statistical mechanics introduced. This concept was introduced by statistical mechanics. Okay, so they try to somehow tie this entropy to chaotic movement inside the system, or chaotic dispersal of energy or matter inside the system. Also, I told you from the last lecture that the change in state would change from state with low probability to state with high probability. Okay, spontaneous process would take place from low probability to high probability, and that is associated with the increase in entropy. So that means if you look closely, the mathematical statement of the second law, this one, is still valid from this interpretation even for the modern statistical mechanics. Let me show you why. This is the definition of entropy, delta S equal to Q reversible over T, which was found or which was derived based on Carnot cycles. Again, during that time, it has no physical meanings. Okay, it's just the derived parameters or derived variables. Now we are going to give this some meanings by using this sentence. If the energy is transferred to the system as heat, okay, we can imagine a box, a system containing gas. Inside the gas, molecules are moving around, okay, creating some certain level of chaotic movement. If heat is supplied to the system, you can imagine that when heat is supplied to the system, according to the first law, internal energy of the gas inside should increase. So therefore, the molecules of gas should move more violently or more chaotically. Okay? So from this animation, you can see that the velocity of each molecule increases, simply representing higher internal energy. And that, as a whole picture, you can see that the whole picture becomes more chaotic. So transfer energy as heat to the system create more chaotic movement, and entropy is an indicator of chaotic dispersal of energy and mass. So in this picture, entropy is increased. Okay? But from the equation, you see that when you supply heat to the system, Q is some number. Q is positive number. And therefore, delta S must be positive. The positive delta S means you have increase in entropy in the system. These two are consistent. So either way, you get the increase in the system entropy by supplying heat to the system. On the other hand, if you supplied energy as work, okay, let me slow down these molecules back to original position. You supplied work to the system, just to make sure you don't get any confusion. So let me supply shaft work, okay? You stir this gas. Imagine stirring the gas in molecular level. Stirring does not increase the speed of each molecule at all. Okay? In macroscopic level, you may see the movement or the flow, the circular movement of the gas inside the tank. But in molecular level, it does not change anything. Molecules still move at the same speed, same chaotic movement. So from this picture, it seems like there's no change in chaotic dispersal at all. Okay? There's no change in entropy as well, because entropy is an indicator of chaotic movement. If you look at the equation, when you supply energy as work, there's no heat. Okay? So Q is 0, delta S is 0. So again, these two are consistent. So supplying work does not change entropy. So these two sentences is again consistent with the second law that heat and work are not equivalent. Okay, so entropy here can tell the difference between heat and work. One makes entropy change, the other one does not. Okay, just like this, they are not equivalent, just like what we mentioned in the part 1 of this lecture 4a. So, as a summary for this second law, we start with the difference between heat and work, the directionality of the process, and then we tie everything to a variable called entropy. Okay, so this lecture we try to explain how entropy was defined and how entropy can be related to the second law. Okay, so mathematically, entropy was defined by this equation, and then this is the second law written in math. The last topics here would be the third law. The third law of thermodynamics is stated here. At absolute zero in temperature, at 0 Kelvin, the vibration of solid stops, and then everything in the molecular level is frozen. If I represent this as cartoon, when you have gas, there's a movement moving around. If you convert gas to solid, molecules of solid remain stationary. It does not move around. However, there's a vibration. Okay, the higher the temperature, the higher the vibration. When you lower the temperature to 0, according to third law, then all vibration stopped. Okay, but arrangement of atoms in solid depends on what kind of solid you are looking for. If the arrangement is random like this, the solid is called amorphous. For crystalline materials, atoms arrange in order like this. And at this point, at 0 Kelvin, there's no vibration and the arrangement is totally ordered. We will define at this stage the entropy is 0. Alright? So, the third law essentially said that entropy of the perfect crystalline material is 0 at 0 Kelvin. By this sentence, it means that we can set at some state the entropy can be 0. So therefore we can say that entropy is absolute value. That means any given state you can calculate or you can obtain entropy of that state as a number. Unlike internal energy or enthalpy, internal energy you cannot say that water at 0 degrees Celsius 1 atm, the internal energy is this number. You cannot say that. You can only say that changing water from this state to another state change corresponds to the change in internal energy by that much. Okay, internal energy or enthalpy are relative number, but entropy is absolute number. We can say right away this water at this state has this much entropy. Okay, so it is big difference between entropy and the rest of the state properties according to the third law of thermodynamics. So this is the end of this lecture 4A. So we talk about all 4 laws of thermodynamics, and next lecture 4B, we will focus on the calculation of delta S and show you the application of delta S. So thank you for watching.